Look up at the night sky for a moment. Every star you see belongs to a galaxy, and every galaxy is drifting through a universe that is getting bigger. Right now, at this very second, the fabric of space itself is stretching. Galaxies billions of light years away are moving farther apart. The distances between cosmic structures are quietly growing across the universe. But here's the mystery. Gravity should be pulling everything together. Over time, the universe should slow down, maybe even collapse. Yet the opposite is happening. The universe isn't just expanding, it may actually be accelerating. So what is pushing the cosmos outward? What invisible force is stretching the fabric of reality itself? In this journey, we'll travel from atoms, to planets, to galaxies, and all the way back to the birth of the universe. And along the way, we'll uncover one of the greatest mysteries in modern science. Why does the universe keep expanding? For centuries, humans looked up at the night sky and imagined the universe as something calm and unchanging. A vast cosmic stage where stars quietly shone and galaxies simply existed, suspended in darkness. But modern astronomy has revealed something astonishing about the universe we inhabit. It isn't standing still at all. In fact, the universe is expanding. Every second, on unimaginable cosmic scales, space itself is stretching. Galaxies drift farther apart, as if carried by an invisible current flowing through the cosmos. The distances between colossal star systems grow larger with time, and the universe quietly becomes bigger and bigger. Now here's the strange part. This expansion didn't just happen in the distant past and stop. It has been continuing for billions of years, steadily reshaping the structure of the cosmos. The universe is still growing even now, at this very moment. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. None of them are traveling across the rubber themselves. The surface between them is stretching. In a similar way, the fabric of space itself appears to be expanding. But this raises a profound mystery. If gravity pulls matter together, shouldn't the universe eventually slow down or collapse? What keeps space stretching across billions of light years? And how did scientists even discover that the cosmos is expanding in the first place? The idea that the universe is expanding might sound abstract at first. After all, no one can watch galaxies drift apart in real time with the naked eye. But astronomers have discovered a subtle cosmic clue hidden in the light arriving from distant galaxies. And that clue tells a remarkable story about motion across the universe. When scientists analyze the light coming from faraway galaxies, they notice something unusual. The light waves appear stretched, shifted toward the red end of the spectrum. This effect is known as redshift, and it happens when an object moves away from the observer. Just like the sound of an ambulance siren changes pitch as it drives away. It's a bit like the Doppler effect we experience every day. When a car rushes past, the sound waves compress as it approaches and stretch as it leaves. Light behaves in a similar way, except the stretching changes color instead of sound. And when galaxies move away, their light becomes slightly redder. What astonished astronomers was the pattern they discovered. The farther away a galaxy is from Earth, the stronger its redshift appears to be. In other words, distant galaxies are receding faster than closer ones. It's as if the entire universe is swelling outward in all directions. This relationship was first recognized by astronomer Edwin Hubble, who realized something profound. The galaxies themselves aren't necessarily flying through empty space. Instead, the space between galaxies is stretching, carrying them apart like raisins in rising bread. But if the entire cosmos is expanding, why don't smaller structures break apart as well? Now here's where the story becomes even more intriguing. If the universe itself is expanding, stretching the fabric of space in every direction, one might imagine that everything inside it should also slowly drift apart. Atoms, molecules, even the particles inside matter, all gently spreading outward. But that's not what happens at all. Down at the microscopic level, the universe behaves very differently. Atoms remain tightly bound together, their electrons orbiting nuclei in stable patterns. Molecules hold their shapes, and matter stays remarkably solid. The reason lies in the powerful forces that govern the smallest scales of reality. Electromagnetism binds electrons to atoms and atoms to molecules. Meanwhile, the strong nuclear force holds protons and neutrons together inside atomic nuclei. These forces are incredibly powerful compared to the gentle stretching of cosmic expansion. Think of it like a tug of war happening across different scales of the universe. On cosmic distances, space slowly stretches like an expanding fabric, but on tiny scales, the bonds between particles act like strong ropes. They hold matter together so tightly that expansion barely makes a dent. It's almost as if the universe follows two different sets of rules at once. On the largest scales imaginable, galaxies drift apart across expanding space. Yet on the smallest scales, the building blocks of matter remain locked together. And that contrast raises an even bigger question about our place in the cosmos. If cosmic expansion affects the universe on its largest scales, a natural question appears. Why don't planets slowly drift away from their stars? Why doesn't the Earth gradually move farther from the Sun as space stretches? After all, our solar system exists inside the same expanding universe. The answer once again lies in gravity. Gravity is the force that binds massive objects together across space. Within a solar system, the gravitational pull of a star is incredibly strong enough to completely overpower the gentle stretching of cosmic expansion. Imagine spinning a ball tied to a rope. As long as the rope is tight, the ball continues circling in a stable orbit. In a similar way, gravity acts like a cosmic tether. It keeps planets locked in their paths around stars. Earth, for example, orbits the Sun at a distance of about 150 million kilometers. That might sound enormous, but on the scale of the universe, it's tiny. At distances this small, gravity dominates completely. The expansion of the universe simply has no noticeable effect. And this isn't just true for our planet. Moons remain bound to planets. Planets remain bound to stars. And entire solar systems remain intact for billions of years. But when we zoom out even farther, something remarkable begins to appear. So how do scientists actually measure something as vast and subtle as the expansion of the universe? After all, galaxies are unimaginably far away, and cosmic distances stretch across billions of light years. Yet astronomers have developed clever ways to turn the universe itself into a kind of measuring tool. And through these methods, they can track how fast space is expanding. One of the key measurements in modern cosmology is known as the Hubble constant. This number describes how quickly galaxies move away from each other as the universe expands. The greater the distance to a galaxy, the faster it appears to recede. It's like watching dots on a balloon spread farther apart as the balloon inflates. To measure this expansion, scientists rely on powerful telescopes. Space observatories like the Hubble Space Telescope peer deep into the cosmos. They observe distant galaxies and analyze the light that has traveled for billions of years to reach us. That light carries clues about distance, motion, and cosmic history. Astronomers also use special objects called standard candles. Certain types of exploding stars, known as supernovae, shine with predictable brightness. By comparing how bright they appear from Earth, scientists can estimate their distance. And when combined with redshift measurements, the expansion of the universe becomes visible. These observations do more than reveal motion across the cosmos. They allow scientists to estimate the age of the universe, which appears to be about 13.8 billion years. They also help predict how the universe might evolve in the distant future. But to truly understand why expansion happens at all, we need to look deeper into the physics of space itself. To understand why the universe can expand at all, scientists had to rethink what space actually is. For a long time, people imagined space as an empty stage where cosmic events simply happened. A vast motionless backdrop against which stars, planets, and galaxies moved. But modern physics revealed something far more fascinating. According to Albert Einstein's theory of general relativity, space is not rigid or static. Instead, space and time are woven together into a dynamic structure called spacetime. This cosmic fabric can bend, curve, and even stretch under the influence of energy and matter. In other words, the universe itself is flexible. Imagine placing a heavy bowling ball on a stretched rubber sheet. The weight of the ball bends the sheet, creating a curved surface around it. Now roll a smaller ball across that sheet, and it will naturally spiral toward the heavier object. This simple image captures the essence of gravity in Einstein's universe. But Einstein's equations revealed something even more surprising. When scientists applied them to the entire universe, they discovered that space-time doesn't have to remain fixed. Depending on the amount of energy and matter inside it, the universe can expand or contract. The fabric of reality itself can grow. At first, even Einstein found this unsettling. He originally adjusted his equations to force the universe to remain static. But observations later showed that the cosmos was already expanding, which means the universe has been stretching its own fabric for billions of years. Billions of years ago, long before Earth existed, the universe looked very different. Vast clouds of gas and dust drifted through young galaxies, illuminated by the first generations of stars. All the while, the universe itself continued its quiet expansion. Yet within these drifting clouds, gravity began to gather matter together. Picture a slowly swirling cloud of cosmic dust. At first, it spreads out across enormous distances, but as tiny clumps form, gravity begins pulling material inward. Gradually, the cloud collapses into denser and denser regions. It's a bit like watching water spiral down a drain. As the flow tightens, motion becomes faster and more organized. In the same way, collapsing clouds of gas begin to spin and flatten into disks. And at the center of those disks, stars are born. Our own sun formed from one of these spinning clouds about 4.6 billion years ago. As the young star ignited, leftover dust and rock continued circling around it. Those fragments collided, merged, and slowly built larger bodies. Over millions of years, planets began to take shape. So even while the universe was expanding on unimaginable scales, local pockets of matter were doing the opposite, collapsing inward. Gravity carved order out of cosmic chaos, allowing stars and planets to emerge. And one of those small worlds would eventually become our home. At first glance, the expansion of the universe might seem like something distant and abstract. After all, galaxies billions of light years away hardly feel connected to daily life on Earth. But in reality, the expansion of the cosmos shaped the entire history of our planet. Without it, the conditions for life might never have existed at all. In the early universe, matter was spread across space in a hot, dense environment. As the universe expanded, it cooled gradually over billions of years. This cooling allowed atoms to form, then stars, and eventually entire galaxies. Without expansion, the universe might have remained a chaotic sea of radiation. Inside the first generations of stars, something extraordinary happened. These stellar furnaces forged heavier elements like carbon, oxygen, and iron. When massive stars eventually exploded as supernovae, those elements scattered into space. They became the raw ingredients for planets, oceans, and living organisms. Earth itself formed from this recycled cosmic material. Every atom in our bodies was once created inside ancient stars. The calcium in bones, the oxygen we breathe, even the iron in our blood. All of it was forged in stars long before the solar system existed. So while cosmic expansion does not stretch our planet apart, it quietly shaped the timeline of the universe that led to our existence. It determined when galaxies formed, when stars were born, and when elements emerged. And when we zoom out to the largest structures in the cosmos, the effects become even more dramatic. Now the scale of the story grows dramatically. Beyond individual stars and planets lie entire galaxies, colossal islands of stars drifting through space. Each one can contain hundreds of billions of stars, along with gas, dust, and mysterious dark matter. And on these enormous scales, the expansion of the universe becomes impossible to ignore. Galaxies are not scattered randomly through the cosmos. Instead, they gather into clusters and vast interconnected structures. When astronomers map their positions, they see something astonishing. The universe forms a gigantic cosmic web stretching across billions of light years. Picture a three-dimensional spider web made of galaxies. Along the filaments of this web, galaxies cluster together in great rivers of stars. Between those filaments lie enormous voids, regions where almost nothing exists. It's one of the largest structures known in the universe. But even within this cosmic web, the expansion of space continues quietly in the background. Over immense distances, galaxy clusters drift farther apart. The web itself slowly stretches as the fabric of space-time expands. The universe grows larger and more diffuse with time. And yet, this expansion has a deeper story hidden behind it. Because if we rewind the cosmic clock far enough, all those galaxies, clusters, and cosmic filaments were once much closer together, which leads us to one of the most profound moments in cosmic history. If we follow the expansion of the universe backward in time, something remarkable happens. Galaxies that are drifting apart today would have been closer together in the past. Clusters would shrink toward each other, and cosmic distances would compress. Eventually, the entire observable universe converges toward a much smaller state. Astronomers believe that nearly 13.8 billion years ago, the universe began in an extremely hot and dense condition. This event is known as the Big Bang, but it wasn't an explosion in space like a bomb going off. Instead, it was the rapid expansion of space itself. Imagine drawing dots on the surface of a balloon again. If the balloon inflates, the dots move apart as the surface stretches. Now imagine reversing that process, slowly letting the air out. All the dots would move closer together toward a smaller and denser state. In the earliest moments after the Big Bang, the universe was unimaginably energetic. Particles formed, collided, and transformed as the cosmos expanded and cooled. Within a few minutes, the first atomic nuclei appeared. Hundreds of millions of years later, the first stars ignited. But here's the twist that surprised modern cosmology. Observations suggest the expansion of the universe is not slowing down as expected. Instead, it appears to be accelerating, driven by something mysterious. Scientists call this unknown force dark energy. When we step back and look at the universe as a whole, one thing becomes clear. The cosmos is not a frozen structure locked in time. It is dynamic, evolving, and constantly transforming across unimaginable distances. The universe is growing, stretching, and unfolding like a vast cosmic story still being written. For billions of years, galaxies have drifted apart through expanding space. Stars have ignited, lived out their fiery lives, and faded away. New planetary systems have formed in the remnants of ancient stellar explosions. And somewhere within this grand unfolding, life emerged on a small blue world. It's a humbling thought when you pause to consider it. Every human civilization, every ocean, every mountain, every living creature exists inside a universe that has been expanding for nearly 14 billion years. We are part of a cosmic journey that began long before Earth ever formed. And yet, within this immense and evolving cosmos, something extraordinary appeared. A species capable of looking up at the night sky and asking questions. A species curious enough to trace the motion of galaxies and the expansion of space. In a sense, the universe has become aware of itself through us. The expansion of the universe reminds us that the cosmos is still in motion. The story of the universe is not finished. It is still unfolding across time and space. And somewhere out there, beyond the most distant galaxies we can see today, the future of the cosmos continues to stretch into the unknown.